When you look at a massive steel column being hoisted onto a skyscraper, the intuitive assumption is its safety relies entirely on raw material strength. It seems the only way this thing comes down is you put so much weight on top that the steel itself physically crushes. But in reality, compression members in buildings rarely fail because the metal yields or pulverizes under the load. The material is almost always strong enough to hold the weight. That raw strength means nothing if the column loses its stability. Instead of crushing, slender compressive elements are taken out by a sudden, catastrophic loss of shape, a failure mode known as buckling. To understand how structural buckling actually happens, we have to look at three things: the perfect myth, the invisible flaw, and the runaway loop. We need to trace a single invisible force, starting from a microscopic misalignment and scaling all the way up to a macroscopic disaster. Because predicting how this specific force escalates mathematically is the only thing standing between a functioning skyscraper and a total structural collapse. In theoretical physics, a vertical load pushes perfectly straight down through the exact center of gravity, the centroid, of a column. This assumes an idealized, perfectly straight member carrying an evenly distributed weight. But in actual construction, a load is never perfectly centered. There is always a tiny, sometimes microscopic offset in how the weight sites. Engineers call this offset eccentricity. In this cross-section diagram, the gap labeled E represents the physical distance between the column's centroid and the downward force, P. Because it's off-centered, this gap acts like a tiny lever arm, introducing a rotational force. That rotational leverage is called a bending moment. It's calculated by multiplying the force by the eccentricity gap. And rather than crushing the steel, this invisible bending moment wants to bow the column outward. In this diagram, the dimension labeled Y max shows the column's center bowing outward, away from the original vertical load path. This creates a dangerous loop. The increased distance creates a larger bending moment, which forces the column to bow even further, repeating the cycle. Engineers refer to this vicious, self-amplifying cycle as the P-delta effect, where P is the compressive load and delta is the growing displacement. This stress distribution graph shows the internal steel. As it bends, the concave side suffers severe compression. The diagonal line crossing the neutral axis shows the convex side stretching into tension. This split makes the column act like two materials, drastically reducing its stiffness. At this point, the structure's own geometry is actively working against it. The changing shape of the column is accelerating its own failure. Long before the steel ever reaches its maximum crushing limit, the exponential math of the P-delta effect reaches a critical mass, and a collapse is mathematically guaranteed. When buckling happens, it's an abrupt, violent release of geometric energy. The steel bows outward in a fraction of a second, without shattering. It does this because of thermodynamics. As the compression increases, the column acts like a tightly compressed spring. Eventually, assuming a bent shape requires less stored energy than remaining perfectly straight under that immense pressure, so the column chooses to bend. The material itself hasn't broken. The steel is still solid, but the structural component has completely failed to do the job it was designed for. In the contest between the physical hardness of the steel and the geometric instability caused by the load, the bending moment always wins. You cannot defeat a bending moment simply by pouring stronger steel. Instead, engineers have to manipulate the geometry of the design to protect against the column's vulnerability to bowing. This slide outlines the primary mathematical defense, the slenderness ratio. Represented by the lambda equation, it directly connects a column's load-carrying capacity to its effective length and the specific shape of its cross-section. To improve this ratio and prevent buckling, you can do two practical things. You can install horizontal bracing to decrease the effective length of the column, or you can use box and I-beam shapes. Those profiles push the mass of the column away from its center, increasing its radius of gyration and stiffening it against bending. Mastering these geometric ratios allowed historical steelworkers to push frameworks higher and higher, taking advantage of steel's stiffness without falling victim to its flexibility. By anticipating the invisible flaw, calculating the P-delta loop, and neutralizing the bending moment, we safely stack thousands of tons of steel into the towering cities of the modern world.